All right. I think we're live.
I'm looking through the Facebook's videos right now. And it won't load now. Yep, okay, so it made a second stream. So we'll just have to go back and like delete that other one.
All right, I think we're live. Hey, it's working. I hear sound.
Yep.
Yay. Okay. Hi, everyone. We are so sorry. The technical issues just, I guess, decided to really compound on us tonight. But it looks like I have sound working. It looks like we are live again. So welcome. This should actually work for real this time. My name is Jessica. I'm the director of the planetarium. With me are Lindsay and Eli, two of my students who work at the planetarium. And the show that some of you may have seen without sound for at least a few minutes is Beyond Bizarre, which is for our Spooktober shows this month. We're going to be looking at the bizarre and strange and awesome weird things in our universe. So for the second time tonight, this time with sound, I'm going to turn it over to Lindsay.
All right. Thanks, Jessica. So Beyond Bizarre is a show that the planetarium has been doing for quite a while, but this past year we kind of revamped it and made it a really cool full dome show. But because it's about bizarre stuff, we wanted to kind of do kind of a low-tech version for you for Spooktober. So we're going to be looking at bizarre things through our entire universe, but we're going to start in our solar system because even though it is, you know, the closest stuff to us, there's still a lot of things we don't know about our own solar system and a lot of things that are mysterious to us. One of those things being the hexagon on Saturn. So you can kind of see the directions of the different wind movements. And there's like a hexagon shape that is forming. This is at one of the poles. So one thing that is strange about this hexagon is that it's really big. One side of this hexagon is the same as the diameter of the Earth. So it's pretty gigantic. And obviously its shape is weird because we have a spherical planet. We would suspect to kind of have circular wind patterns and shapes, but we have these straight lines that make a hexagon, which is just really strange. This has been tested in a lab actually, but in this case we don't have any atmosphere or gases. This is just water. And so we have green dye put into the water. And so we have the inner circle going kind of slower and then the outer circle going faster. And it just so happens with that difference in velocities, it's a very big difference in velocities, that it just so happens that a hexagon starts to form. And it is in a circular tank. Another bizarre thing in the solar system is Io, a moon of Jupiter. So this is Io. We often call it the pizza moon here at the planetarium, you know, yellow for cheese and pizza sauce and sausages or olives, but I don't like olives, so sausages. Well, what's really cool is these sausages.
Hey, Eli fought me over that one last time.
Yeah, they've heard our discourse on olives versus sausage.
Yeah, thanks. So these sausages are actually volcanoes, and Io has over 300 volcanoes on the surface, which is really cool. It's the most volcanic object in the entire solar system. So definitely one of the most unique things in the solar system. Another moon of Jupiter is Europa. It has an icy surface, and you can see cracks in the surface. And in those cracks, or when they form, they are filled in from underneath from a liquid water ocean. So that is one actual piece of evidence that it is liquid water underneath this surface, is that those cracks get filled in. And also, so we think that it is being warmed on the inside by tidal heating. So what tidal heating means is, so on one side of Europa, there's Jupiter, and it has a lot of gravity. And then on the other side of Europa are some pretty big moons also. And so these moons and Jupiter are kind of in a tug of war. And this causes friction on the inside of Europa, and that friction causes heat. Now, what's really cool about Europa is that we actually think there could be life there, because, you know, we need liquid water to survive. So there could be some things living in the liquid water oceans at Europa. So there's actually more water on Europa than there is on the entire Earth, which is just crazy because it's super tiny. So here it has an iron core, a silicate or kind of rocky mantle, a subsurface ocean, and then that thin crust of ice on the surface. Enceladus is a moon of Saturn, and it's a little bit similar to Europa. It also has an icy surface and a global ocean underneath the icy surface. But the reason we know Enceladus has this ocean underneath the surface is because of these cryovolcanoes. These are shooting liquid water up through these cryovolcanoes, so there must be liquid water underneath them. So this is actually another place where we could be looking for life in our very own solar system. So now we are going to move out a little bit further away from our solar system and take a look at some cool things we can find in the Milky Way galaxy. So first we're going to look at some cool exoplanets, but first we kind of need to know how to find exoplanets, because that kind of contributes to the things that we can find out about exoplanets and what we can learn about them. So this video is going to go through the different ways that we go about finding exoplanets.
Believe you me, we've seen a lot of movies. And eating the small bits of cheese stuck to a McDonald's
Not
wrapper.
sponsored, unfortunately.
No, we are not sponsored by McDonald's.
But open to the idea.
They are nestled in the final frontier. Countless worlds, scattered throughout countless galaxies, challenge the notion that we are alone in the universe. Exoplanets are worlds that exist outside of our solar system. Also known as extrasolar planets, these bodies often orbit their own stars, with some being a part of entire planetary systems. Exoplanets are made of the same elements as the worlds in our solar system, and based on their composition and structures are just as diverse. Some, known as giant or Neptune-like planets, are large gaseous worlds. Other gas giants, called hot Jupiters, closely orbit their stars, causing the planets to have high surface temperatures. Another category of exoplanets consists of super-Earths. Smaller than the gas giants, but larger than Earth, super-Earths are terrestrial and made primarily of rocky or icy material. The final category includes Earth analogs. Much as their name implies, Earth analogs are similar to Earth in various ways, including size, composition, and distance to their home star. Exoplanets are difficult to detect directly, mostly because they are outshined by the stars they orbit. To circumvent this, about 5 primary methods have been developed to find these planetary bodies, including radial velocity, in which a planet causes a star to wobble; direct imaging, where the glare of stars is blocked in order to see objects nearby; astrometry, which observes the star's movements in relation to nearby stars; gravitational microlensing, which observes the light of a star being bent by a planet's gravitational pull; and the most prolific form of finding exoplanets, transit, the method in which a planet passes between its star and Earth, thereby dimming its star's light. Scientists have suspected the existence of worlds outside of our solar system for thousands of years, but the first confirmed existence of an exoplanet orbiting a sun-like star only occurred in 1995. Ever since, about 4,000 exoplanets have been confirmed by multiple discovery methods, with about 3,000 more awaiting verification. According to one theory, at least one exoplanet orbits each star in the Milky Way. This would place the exoplanet count in our local galaxy to about 1 trillion. The search for exoplanets continues, not just to create a catalog of known worlds, but also to see if life may exist elsewhere in the universe. Astrobiologists closely study the size, composition, and location of exoplanets relative to their stars to see the likelihood of organisms thriving in an environment other than Earth. Who knows what discoveries these new worlds could bring?
So one of the things that we're trying to learn about exoplanets that they mentioned is the composition of these exoplanets. And so the way we do that is we have the light from whatever star it's going around. Sorry. And as the light goes through the atmosphere of whatever planet it is, whatever molecules or elements are present there absorb specific wavelengths of light. And so, like with this band gone, we know that there's oxygen on this particular planet, whatever it is. These bands mean that methane is on that planet. So that's partly how we try to figure out what the surface of these exoplanets is like, and if anything could possibly live there.
So we actually did get a question that I want to get in here. So the question is, in our solar system, are all moons formed the same way? What things determine the composition of the various moons?
Oh, good question. So not all moons are formed in the same way. Our moon is kind of unique in the way that it formed. There was a Mars-sized object that crashed into the early Earth. Debris from that impact ended up in orbit around the Earth, and then slowly came together to create our moon. I don't think there are any other moons in the solar system that were created in that way.
Pluto's moons.
Pluto's Sharon. Okay, so Pluto's moon's also that way. Mars's moons are actually captured asteroids. So there were just some asteroids passing by, and Mars captured them with their gravity. And then some other moons around some of the bigger planets just kind of formed from the debris left over from planet formation, right, Jessica?
Yeah, they formed around the forming planet. That's kind of like a mini solar system.
Yeah. So very similar to how our planets formed and the debris kind of left over after the sun formed, the debris left over from planet formation formed moons.
And the majority of the moons around the big planets are, like Mars's moons, captured objects, either captured asteroids or captured comets. But that's a great question.
Yeah, so if they're captured asteroids, they're going to be more rocky. But like you could see with Io and Europa, moons come in many different compositions. Yeah. Okay, so this exoplanet has the best name, GJ 1214b. We name these exoplanets after the star they're orbiting around and then whatever order they were found in. So since this is B, this was the second exoplanet found. Anyway, so it's about 3 times larger than Earth. So this was kind of one of those super Earths that they were talking about. But it actually has an ocean 7 times larger than the Earth's, even though it's only 3 times larger. Water is about 10% of this exoplanet's total mass, but Earth's water is only about 0.05% of its total mass. And we think that this ocean could be hundreds of kilometers deep. 55 Cancri E is really super cool. This is the diamond planet. We think that about 1/3 of this planet is made up of diamonds. This planet's diameter is about 2 times bigger than the Earth, but it's much more dense. Its mass is 8 times larger. And it orbits its star really, really fast. It only takes this planet 18 hours to complete an orbit around its star. The last one we're going to look at is Karat 7b. So this planet is about 2 times the size of the Earth, and it orbits very, very close to its star. So and it's tidally locked. So one side of this planet is facing the sun all the time. And on that side of the planet, it gets up to 2,600 degrees Celsius. So probably no life on this planet.
Also, just a quick plug, if you are interested in a more in-depth look at exoplanets, we have done an entire show about it that you can go back and watch. Sorry, Lindsay, continue.
Yeah, we also have done a show about life. That's one of our favorite things to talk about, so. Okay, red rectangle nebula is a weird thing that we see in our galaxy. It's just a red rectangle. Scientists aren't super great or creative at naming things. They just name them after whatever they look like. And so at first, this might not really occur to you that this would be a weird thing to see out in the galaxy. So first we need to look at how nebulas are usually formed. And this is a particular type of nebula, so how planetary nebulas are formed.
Don't let the name fool you. A planetary nebula has nothing to do with planets. When astronomer William Herschel discovered the Saturn Nebula about 200 years ago, he named it a planetary nebula because the faint blue-green tint and round shape reminded him of his recent discovery, the planet Uranus. Basically, a planetary nebula is a glowing shell of gas and dust expelled by a dying star. When a low-mass star at the end of its lifetime expands into a red giant, as it burns through its fuel, it will eventually collapse into a white dwarf. Therefore, the star will throw off its outer layers, forming a nebula which is often the shape of a ring or bubble. This expanding shell of gas will last about 20,000 years before spreading out into the deep space.
Okay, so he said that this gas that expands as a planetary nebula is usually like ring shaped. And so that's why this red rectangle nebula is so strange. We're not really sure how this particular planetary nebula could have formed as a rectangle instead of a ring like most other ones. This video is going to kind of show you a simulation of one idea about how that happened, and that there's debris kind of surrounding the nebula, and so that kind of prevents part of the nebula from expanding out into a ring. Pretty cool. Next, we are going to talk about neutron stars. So neutron stars actually form during a different stardust. So we just talked about planetary nebulas, and those occur after a kind of medium-sized star dies. Neutron stars are what forms sometimes when a larger star dies. And so this is the Crab Nebula specifically. So there's a really big star. There's a supernova explosion. And then the leftover star in the middle is a neutron star. And then we have all of this other debris coming away from the star in the explosion. So neutron stars are named that because they're made of neutrons. Again, scientists not super creative with the names. There's a solid crust, and then we have this liquid interior that's mostly neutrons. And neutron stars, as I said, are really small. The mass is about 1.5 times the mass of the sun, but it's only 12 miles in diameter. So really, really dense. If a neutron star is rotating, it is then called a pulsar. So this shows a neutron star and its magnetic field and some jets that are coming out from the neutron star. And since it's rotating, our view of those jets kind of changes as the neutron star goes around. Usually, this is really slowed down. Usually, neutron stars rotate several times a second. The fastest pulsar that we found so far spins around 1,600 times per second. So that is crazy. Okay, this is a Mega Centauri. It is a cluster of stars. Star clusters are one of my favorite things to look at through the telescope because they just look like pretty little diamonds all scattered over here. So Omega Centauri is strange because it's a pretty big cluster for being a star cluster. And so since it has more stars in it than other clusters that we find in our galaxy, we think that maybe this could have been a separate galaxy at first, just a small one, and then it kind of became a part of the Milky Way, and that's why it has so many stars in it. Now we are moving out to the rest of the universe. So Stephen's quintet is a group of 5 galaxies that are all gravitationally bound together. Because of that, these galaxies could possibly collide and merge together at some point in the future. It would still be like at least millions of years. So Hoag's object is this galaxy that has a ring around it and then this kind of white ball in the center. So the reason that it is weird is because of this kind of, well, a couple of different reasons. So this ring is mostly blue stars. Now, blue stars are really, really hot, and so they burn through their fuel really fast. So if an area still has blue stars, it's kind of a young area. But you can see in this central area, there aren't any blue stars there. So that area is older because all of the blue stars have already died. So that's weird how we have such a dichotomy between the center and the outside. And then also what's weird is that there's this gap between them. We're not really sure what's causing that gap. It's possible that these were two separate galaxies that ended up merging together, or it could also be possible that any stars that ended up orbiting in this area just were not stable and got flung out either to the outer ring or out into space. Next, we are going to talk about gravitational lensing. Okay, so this is the Hoag's object that we were just looking at, the galaxy. So this is an Einstein ring. It is not a galaxy like Hoag's object. It is an effect of gravitational lensing. So the mass of this white area here is causing a blue galaxy from behind it, that light, to be warped around. So here we have kind of a massive star cluster. Here is the galaxy back here. So this massive star cluster warps the fabric of space-time. And because it warps the fabric of space-time, it can bend light around it. So we see distorted light rays around the massive cluster.
This same light bending leads to the warping of light from distant galaxies as the light encounters supermassive galaxies on their path to us. This is called gravitational lensing. Here's a clip that shows how this lensing works on a grand scale. A distant galaxy would be seen here on Earth directly if there were no intervening massive cluster to bend the light. But with such a cluster, the light from the distant galaxy gets bent into rings and arcs to continue on to the Earth. This is Abel 1689, 2.2 billion light years away. It's one of the most massive galaxy clusters known. The gravity of its trillion stars plus dark matter acts like a 2 million light year wide lens in space. And here's another cluster, 5.7 billion light years away. It's the latest from Hubble on gravitational lensing, released in late 2015. These foreground galaxy clusters are magnifying the light from the faint galaxies that lie far behind the clusters themselves. These faint lensed galaxies are around 12 billion light years away. It's the gravitational lensing that allows us to see that far back in time. Without the magnification, these galaxies would be invisible for us.
So here's that picture of the cluster that we just saw in the video. So we have that massive cluster, and we can see light in the form of rings from galaxies that are behind that cluster. So that's really cool in itself. But what also is cool about this picture is that with one picture, it proves that massive objects bend the fabric of space-time and affect the movement of light. Okay, last but certainly not least, black holes. Dun, dun, dun. Okay. So this video is going to kind of show you how the black holes end up forming and some of the kind of unique things about them.
Black holes are incredibly fascinating. I mean, they are invisible beasts lurking in space, sometimes ripping passing stars in half, scattering their remains. But how do they form? First of all, they are definitely not holes, so don't let the name fool you. Rather, they are a great amount of matter packed into a very small area. If we use some analogy, a black hole is basically like a star, 10 times more massive than the sun, squeezed into a sphere roughly the diameter of New York City. Therefore, its gravity is enormously strong. However, different types of black holes form through different processes. Stellar mass black holes are born when very massive stars, tens of solar masses, can no longer produce energy in its core, so they explode in supernovae. These explosions are some of the most energetic phenomena in the universe. So after the outer layers of a dying stars are violently ejected into space, the remaining core collapses under its own weight to form a black hole.
Okay, so when we were talking about neutron stars, I said that sometimes the end result of a supernova explosion is the neutron star left over. But if that is leftover stars 3 times the mass of our sun, then it can't hold itself and it collapses under the weight of its own gravity and becomes a black hole. Oops. So we actually have a picture of a black hole now. This is actually a supermassive black hole that is at the center of the galaxy M87. We are not really sure how supermassive black holes at the center of galaxies form quite yet. It could be that some of those stellar black holes formed from those supernova explosions kind of combined together to make bigger and bigger black holes. That's one idea about that. But yeah, this is super cool. This ends up looking like what we thought it would look like. Jessica, do you have anything to add?
Not that I can think of.
Mm-hmm.
There's still so much that we just don't know about these.
Mm-hmm. I haven't heard, besides the image coming in now, I haven't heard of any other data coming from this yet.
Not any that they've released. I know they were also doing it for the supermassive black hole at the center of our galaxy.
Okay.
But the data they had wasn't very good quality, so they weren't able to get an image like they were for M87. But I know that they're trying to get better quality data to do that.
Cool.
All right.
Eli, did we get any other questions?
Nope, no other questions.
Well, if you do have any questions, now is a great time to leave them down in the comments for us. I just once again want to say thank you everyone for being patient as we dealt with tonight's technical troubles. I think Eli made a good point while we were transitioning in between, trying to scramble, that we've been doing this since, what, April? The beginning of April?
Yep.
Yeah.
And this is the first major technical problem we've had, so fingers crossed we've been doing good. But yeah, let's see. Let me tell you a little bit about what is coming up over the next week. So we are not doing a show on Saturday. We are taking the day off. I'm getting married on Saturday, so we are taking that weekend off because I don't want to work. So, but we will be back next week with our regular Wednesday, Saturday schedule. So Wednesday, we will be doing the history of Halloween, which Eli is going to tell us all about. And then on Saturday, we are doing our first ever PG-13 star show called Bloody Skies. So it's the constellation stories, but probably not as you've heard them, because most of the stories have been greatly altered so that they can be family friendly. So we're going to tell you some of the more true versions.
More accurate Greek stories.
Yeah, we're not we're still not going all the way because that would be an R-rated show, and we don't want to do that. But we're very excited for it. We hope it's going to go well. If you are interested in those sort of stories, but more family-friendly version, we did that last weekend with spooky star stories to tell in the dark, so you can always go watch that. And all of this is leading up to Halloween, where we are going to be doing Halloween outside the planetarium on Saturday, October 31st from 3 to 5. This is going to be a drive-through event. So we will have our guests kind of drive up to a couple of different stations where we will be handing out goodie bags full of fun activities of things that look like magic but are actually science. And then we'll also have a couple of demonstrations along that kind of same theme. And we'll be doing some other fun things too, like seeing what happens when we drop a pumpkin off the roof, in the name of science. So we're very excited for this, and we hope you can come out and join us. It looks like we had a question.
Yeah, about a meteor shower on November 7th. I'm not finding anything about it. I did a quick Google search. I'm not finding anything that's really popping out at me. But I'm sure if there's something, we'll cover it in What's Up November.
Yeah, we will. I don't know. Yeah, I also don't know about one coming up in November. It looks like
The Leonids are
the
November 16th to 17th.
yeah, that might be what you're asking. The
That's
Leonids.
the only meteor shower that I can find that's going to happen in November.
Yeah, but with in general though, if you want to observe a meteor shower, generally you want to be later at night. Typically after midnight is when you have the kind of peak, the most meteors per second or per hour, not per second. Well, I guess it's technically true too, but you also want to just try and get to as dark of skies as you can. So I know a few good places near Duluth that we often recommend are Brighton Beach and Hawk Ridge. They have pretty decent dark skies to see. Other than that, even just driving a little bit out of the city will be good. But yeah, we'll definitely cover more to talk about that in detail in the What's Up November.
I did find out that the Orionid meteor shower usually ends on November 7th.
So ends, but doesn't peak then.
Right.
Yeah, I'm finding
Okay.
here that the Orionids peak on the 20th of October.
Yeah, I believe we talked about that one in our What's Up October. It's actually, so honestly, just about any night, if you get to a dark enough skies and you watch for long enough period of time, you will see a couple of meteors.
Yep.
We always have stuff that is falling through our atmosphere. But yeah. All right. I don't see any other questions. We are definitely ending a bit later than normal. But again, thank you for being patient with us. We hope you did enjoy the show. And we will see you next week with Hysteria of Halloween and Bloody Skies. So have a great week, everyone, and we'll see you next time. Bye.